Hello, dear students. I am Samir Velankar. I welcome all of you to this third video on the topic asymptotic notations. In the first video, we saw if a function fn is less than or equal to another function gn multiplied with some constant, then we say fn is big O of gn. And in the second video, we saw that if a function fn is always greater than or equal to gn multiplied with some constant c1, then we say fn is omega of gn. So O notation gives upper bound of a function. We say fn is always below gn. So gn is always upper bound of fn, and omega gives lower bound of a function. So if fn is always greater than or equal to gn, that means gn is always lower than fn. So gn is lower bound of fn. Now in this video, third notation, and possibly the most important of all three notations, is theta notation. So let's find out what is theta. Now, I trust me that this notation is going to be very easy after learning O and omega, because this is combination of both O and omega. Now just check. If Fn is theta times Gn, theta of Gn, somebody tells you that Fn is theta of Gn, then it means that Fn is always less than or equal to C1 times Gn. Wait a minute here. Just check this portion which I am marking. Fn is below C1 into Gn, below, less than or equal to C1 times Gn. You tell me, isn't this portion meaning that Fn is big O of Gn? Are you understanding really? Because we are saying Fn is less than or equal to C1 times Gn, isn't it? And what's the other part? The other part is Fn, check what I am marking, Fn is greater than or equal to C2 times Gn, isn't it? Just check the other part. Fn is greater than or equal to C2 times Gn. You watch, if it is written like this, then this means Fn is omega of Gn, because we are claiming that Fn is greater than or equal to C2 times Gn. So Fn is both less than C1 times Gn and Fn is greater than or equal to C2 times Gn. That means Fn is O of Gn is true, and Fn is omega of Gn is also true. In short, Fn is equal to theta of Gn if Fn is big O of Gn and Fn is omega of Gn. If both are true, then Fn is theta Gn. Okay, let's see what does that mean. By the way, with some examples we'll see, of course. By the way, this relation which I am marking is true for some positive constants C1 and C2. Now here there are two constants, because on at one side Gn is multiplied with C1 and at other side Gn is multiplied with C2, and this is true for n greater than or equal to n naught up to infinity. From n naught it is true up to infinity for any value of n. Let's take an example. Suppose, example 1, suppose fn is n square, let's say, and gn is 3n square plus 4n plus 1. Now somebody asks us, is n square less than or equal to 3n square plus 4n plus 1? Is this true? This is fn and gn is 3n square plus 4n plus 1. Is this true? Yeah, indeed it is true, because left hand side fn is having only n square and right hand side is having 3n square. Watch that. This is true, isn't it? Indeed. So the constant 1 is enough over here. I hope you are understanding. So by proving this, we have proved that fn is big O of gn for constant equal to 1. Hello, the constant c1 we have taken here is 1. But then is n square, it is asked, is the same function n square greater than or equal to 3n square plus 4n plus 1. Is this true? Is Fn, I'll just scroll down, is Fn greater than or equal to this Gn? Now, you know it's not directly possible, but we are allowed to multiply Gn with a constant. And you know from the previous video, we can take the constant as 1 by 8. And this is indeed true, isn't it? This is true. That means Fn is omega of Gn. Provided the constant C2 is the constant now, is 1 by 8. Is 1 by 8. So for some constant C1 and C2, we are able to prove that n square is below 3n square plus 4n plus 1, and n square is greater than 3n square plus 4n plus 1. That is, n square is less than and n square is greater than same function Gn. Then Fn is theta of Gn. I hope you are understanding, isn't it? So coming to what I have written in black here, just check that it can be proved that Fn, which is n square, is less than or equal to 1 into Gn. Given the Gn is 3n square plus 4n plus 1, and Fn is greater than or equal to, this Fn is greater than 1 by 8 times Gn. Same function Gn, 3n square plus 4n plus 1. Then Fn is theta of Gn, provided C2 constant is 1 by 8, C1 is 1, and this is true for all values of n greater than or equal to 1. Watch. So Fn is theta times C. Let's see a very interesting example now. Example 2. Here we go. You should instantly get this, and you should be able to say that theta cannot be proved here. Let's see, Fn is n square, and Gn is 3n cube plus 4n square plus 2n plus 1. So somebody asks us, is n square less than or equal to 3n cube plus 4n square plus 2n plus 1? At the same time, is n square greater than or equal to the same function, 3n square plus 4n square plus 2n plus 1? This should be true for both, provided you get some constant here, say it is C2, and provided you get some constant here, say it is C1. Now you know you can't prove this. Why? Because this portion which I am marking is n square less than, watch, is n square less than 3n cube plus 4n square plus 2n plus 1? Of course this can be true even with constant 1, because n square, come on, n square is having a degree 2, and 3n cube on the right hand side will defeat n square. So definitely Fn, that is n square, will be less than or equal to Gn. This can be proved. That is, Fn is equal to OGn can be proved with constant equal to 1. But is this part which I am now marking, is this possible? Just check this. Can n square be greater than or equal to 3n cube? I am so sorry, I made a mistake here. 3n cube plus 4n square plus 2n plus 1. Impossible. This cannot be proved because n square is having lower degree, and 3n cube, you watch, the Gn is having higher degree. So you just can't force this relation to be true for any constant. I hope you are understanding. You cannot prove, this is not true, that Fn is omega of Gn. As Fn is not both O and omega of the same function, we say that Fn cannot be theta of Gn. I hope you got this. So when can you prove that Fn is theta of Gn? Come again. Fn is theta of Gn if Fn is O of Gn and Fn is omega of Gn. That is, Fn, watch this observation, Fn is having equal degree as compared to Gn. Then only you can prove that Fn is theta of Gn. Whereas Fn is not theta of Gn if degree of Fn and degree of Gn are different. Watch one more example. Watch this example. Suppose I have Fn as n plus 1 and I have Gn as n square plus 1, let's say. And you are asked, is Fn theta of Gn? You are asked this. Straight away say no. False. It can't be. It can't be. Just check. Be very careful in understanding this. Why this cannot be true? See, for this to be true, for Fn to be equal to theta of Gn, Fn should be below n square plus 1 and Fn should be greater than or equal to n square plus 1. Both with some constant, isn't it? Now, this left hand side over here is indeed true. N plus 1 is below n square plus 1. Come on. But how can you make this right hand side, this portion, true? I mean, n square plus 1 can never be less than n plus 1. How can it be true, isn't it? For any constant. So it can't be proved. Why it cannot be proved? Because Fn was of degree 1, n plus 1, isn't it? N plus 1. So it was of degree 1. And Gn was n square plus 1, degree 2. Degrees were unequal. So you can't prove Fn is theta of Gn. I hope you got this. So we say theta notation, gives tight bound of the function Fn. It gives tight bound of the function Fn, isn't it? If we say Fn is equal to theta of Gn, it means Gn is tight bound of Fn. Or we can say Gn is almost same as Fn, almost same, because both are having same degree. Correct? Both are having same degree. I hope you are understanding. If somebody tells you that Tn is theta of n square, suppose, then you know t is a function of n, like f of n. T is a function of n. And this n square written inside this theta notation is a function of n. N square is a function of n. Then what you understand is surely this Tn, must have been some polynomial like n square plus 1. Definitely. Because it is of theta of n square, both are having same degree. Tn and n square are having same degree. Maybe Tn was 3n square plus 1, whatever. But the degree of Tn and degree of Gn are equal when we say theta notation. Whereas if somebody tells you that Tn is On square, suppose, On square, then you know Tn is less than or equal to n square. So T is a function of n. Then Tn can be even n plus 1. Because n plus 1 is less than or equal to n square. Any function which has degree less than or equal to degree of Gn makes the O notation true, isn't it? Isn't it so? Now, suppose somebody tells you Tn is omega of n square. Then what it means is that degree of Tn is greater than or equal to degree of n square, because omega means Tn is greater than or equal to n square. So if you have 3n square plus 1, this is Tn. This can be Tn, I am saying. This can be Tn because it is greater than or equal to n square. Degrees are equal. But this can be 3n raised to 4 also. Because 3n raised to 4, the degree is 4 here, will be greater than or equal to n square. Okay? But repeating it. But if you are told that Tn is theta n square. Now you see how clearly Gn is given. Gn is n square. But what is Tn? You are not given. What was that polynomial? But whatever it is, you are sure that the polynomial had degree 2, 2 and only 2. It can be degree 2. It can be something like 3n square plus 4n plus 1. Only then, if the degrees are equal, you can prove that one is theta of other. That's the theta notation, the tight bound. So, rewinding it very fast, Fn is OGn means Fn is below Gn. Fn is omega Gn means Fn is above Gn. Fn is theta Gn means Fn is tight bound of Gn. Fn and Gn have same degree. Fn is almost same as Gn. Thank you very much.